Welcome back to NE 630, Nuclear Reactor Theory. So last couple of lectures we were doing the same business again and again, and we were calculating the neutron flux distribution in the fast energy region, intermediate energy region, and we showed that in the fast energy region goes like chi of energy E over sigma total of energy E. If we consider above 1 million electron volt, sigma total is nearly constant, so the neutron flux distribution will go like chi of E. And in the slowing down region, we showed that the flux distribution will be 1 over E modified by two things. The first one is absorption attenuation, or attenuation due to absorption, and this factor is just exponential factor, and the other factor is just 1 over sigma absorption of energy E plus sigma scattering of energy E. For hydrogen, for example, or for non-hydrogen will be sigma scattering. So two things modify the energy distribution of the neutron flux in the slowing down region. The shape of the cross-section, the sigma absorption, and the sigma scattering, and the other thing is the absorption from the above lying layers. So today we will go to the last part of the energy distribution, which is the thermal energy, and we will show that it is Maxwellian in shape. So let's do this and move on. So again, we will discuss the neutron energy distribution in the thermal range. And the main and big difference between the thermal energy region and the rest of the energy regions is in the thermal energy region, the cutoff for the thermal energy region is 1 electron volt. And the lowest energy is, of course, 0. And let's assume that, like before, we want to do the neutron balance at energy E within delta E. So usually, in order to do the neutron balance, we said, okay, we studied the neutron scattering from energy E prime within delta E prime. Yes, guys? And we said that in the previous two energy regions, we stated that the neutron balance is just whatever absorbed at energy E and whatever scattered from energy E, yes guys, will be equal to the sources that come to the energy E from energy E prime. And when we did this for the last two lectures, we said that this should be coming, if you are coming to E, so the upper energy will be what? E over alpha, and you are coming from sigma scattering of E prime, phi of E prime, divided by 1 minus alpha, multiplied by E prime, dE prime. This is not true in case of the thermal energy region. Can somebody tell me why? The upscattering. So it's very complicated in the lower energy region, in the thermal energy region. This is not in the thermal energy region, guys. This is not in the thermal energy region. This is just in the upper energy region, in the high energy region above the thermal energy. So this is in the fission region and the slowing down region. In the thermal region, we will not be able to use this formula here, especially for the scattering cross-section. Why? Because imagine that you have let's assume that you have something like a spring, and there is a ball at the end of the spring, and you start pulling this ball like this, so the ball will start oscillating between two locations, and this is the equilibrium position. equilibrium position. And then there is two cases. Assume there is a cannon gun that's sitting there and shooting another ball with very high speed. And then assume that there's another ball, somebody is sitting here, and he throw a similar ball this direction. What's the difference between those two situations? So this velocity is huge compared to this. So this guy, in the frame of reference of this guy, will look at this as if it does not have any oscillation at all. Why? Because the frequency of oscillation, even if it is high, the velocity is very small with respect to the huge velocity. So it sees this oscillating nuclei as if it does not oscillate and it is free. If you study nuclear physics, this is exactly the same for the case of Compton scattering. In Compton scattering, the electron will look at the other electron, bound electron. A free electron will look at bound electron in the nucleus, in the atom, as if it is not bound at all. It will look at it as a free electron, and this is why we were able to apply the laws of classical mechanics in collisions. So we apply the conservation of energy and conservation of momentum, and we got the factor or the formula for the Compton scattering formula. Yes? But if the energy is very low, now it's very complicated. What do you think at the very early beginning? It was bound, it was free. It's not free, it's bound, and there is quantum mechanical effect that will take place here. So in this case, at low energy, we cannot apply the Compton scattering in atomic collision. We apply whether it is photoelectric effect or Thomson scattering or stuff like this. Scattering that's low energy, not like Compton. Compton, there is a threshold of 1.02, no, higher energy, not a threshold, 100 kilo electron volt or above for Compton scattering. But for low energy, no. So this is exactly the same. Low energy neutron, the nucleus now is in the water, and it has oscillation in the water itself. So this oscillation, there is crystal structure for water, or there is a crystal structure for water. The atomic collision now, this atom will be jiggling around. So you will have oscillation, you will have vibration, and you will have rotation. So this nucleus of the atom of hydrogen or of water or whatever, this nucleus will now acquire energy from collision with different nuclei in the medium, and maybe the energy of this nucleus will be more than the energy of the neutron that has the similar energy. So in this case, maybe the nucleus will be coming from the oscillation this way. It will meet this guy and then give it energy in this direction, and it raises its energy. So this is called upscattering. So the other thing is, at low energy, you knew that there is the Broglie formula, and the Broglie formula states that with every particle moving with a momentum p, there is an associated wavelength lambda given by h over p. And p is just m multiplied by v, where v is the velocity. So if your velocity goes down, your wavelength goes up until it becomes comparable to the crystalline structure of the material. Then there is lots of other phenomena like what? Like wave interaction with the matter. So there is interference, there is diffraction, there is wave interaction with the material. So now the cross-section will be extremely complicated. It's not the normal cross-section. Because of those complicated diffraction and interference pattern and all those stuff, it's difficult to calculate the cross-section. And also the scattering cross-section will not be given simply by sigma scattering, the sigma scattering multiplied by P of E. So it will not be given by the simple formula sigma scattering over 1 minus alpha multiplied by E. It's not It's not given by this, so I cannot write this anymore. Now we have to do neutron balance to see what's going on. So our neutron balance now, our neutron balance will be just, again, if this is energy E prime also might be lower than energy E, and now I will have neutrons coming from lower energies to my energy now, and now I can get scattering, up scattering and down scattering to the energy E. It's not like before. Before I have only down scattering, but now I can get up scattering, or I can get down scattering. So there is two types of scattering collisions now. So if you write the balance equation for neutron balance equation, so let's write the neutron balance equation. So what will be the neutron balance equation? The neutron balance equation will be just the absorption at the energy E plus the scattering at the energy E multiplied by the flux at the energy E will be equal to what? Again, it will be equal to what? Down scattering and up scattering. So it will be equal to sigma scattering from energy E prime to energy E multiplied by phi at energy E prime dE prime. Now, where is my integration will be carried over? 0. This limit is E thermal. So it will be 0 to what? 0 to E thermal. But now I am missing another part. What's the other part? Now I said, excuse me, what's absorbed here plus what's scattered from here, this is the losses. The source is what's coming from energy E prime, whether it is up scattering, down scattering, or up scattering. But I am missing something else.
Fission?
No, fission, there is no fission at this energy.
Scattering from epithermal?
It's scattering from the epithermal. So there is some neutrons that come from directly from here to the energy E. And this is the source S of E. So this is what? Slowing down source. Okay guys? So this plus is after this one. So nobody can say where is this. So this is equal to this term plus this term, and this term is just slowing down source. So you knew what's this source. It's the source that come from slowing down. Okay? All the neutrons that slow down up to the energy E. And this slow down is actually what? Is related to the slowing down density. I cannot put slowing down density because slowing down density is what? Is per unit. Okay, I can put actually because it is per unit volume. So I can put it. Okay guys? So now let's assume that there is no leakage in the system. There is no leakage and no absorption. Or let's assume first, instead of no leakage, let's assume that there is no leakage and no upscattering above, E thermal, no upscattering, above E thermal. So above the energy E thermal, if the energy is here, there is no upscattering. It's upscattering only in the thermal energy region. Above, there is no upscattering. So if there is no leakage in the system and there is no upscattering, So any neutrons slowing down up to the energy E from the moderation region, they should be absorbed in this region. Yes? Where they will go? There is no leakage. Yes? And there is no upscattering that they will return back up to the region, this region again. So what's the condition now? Condition is Q at energy E, which is the slowing down at energy E, just equal to what? At energy E thermal. So Q at energy E thermal, slowing down beneath the thermal energy, should be equal to what? 0 to E thermal sigma absorption of E, sigma absorption of E multiplied by phi of E dE. What does it mean, this equation? Can somebody tell me what's the physical meaning of this equation?
All the neutrons coming below E thermal will be absorbed.
Yes, all the neutrons coming below E thermal, slowing down from the slowing down region, beneath E thermal should be absorbed. In case they satisfy what? No leakage and no upscattering. Yes, guys? So now, if now I will assume that there is no absorption and there is no source of neutrons coming from the moderation region, what will be the balance? So no absorption, the absorption term here is 0, so this is sigma scattering of what? Of E, phi of E, equal to, what's the scattering term?
Integration
0 to what?
E thermal.
0 to what? E thermal, sigma scattering of what? E prime goes to E multiplied by phi of what? E prime dE. I just stated that there is no upscattering. So the upscattering above the E thermal is what? Is 0. So it does not hurt me if I change this to what? Yes? Why? 0 multiplied by anything from E thermal to infinity, it does not add anything to your integral.
And we're still assuming no leakage.
Yeah, no leakage. Yeah, no leakage. So what does this mean? Can somebody tell me what's this? Sigma scattering at energy E multiplied by phi of E. What does it mean?
Scattering events at E.
Scattering from the energy E. Sigma scattering at energy E prime, whether it is up or down scattering, phi of E prime dE prime from 0 to infinity. What does it mean?
Scatters to energy.
Scattering too. All the scattering too. So this is just a balance equation. It tells me that in the absence of absorption and in the absence of leakage, all the neutrons that comes into the energy E, they should leave this energy E. And this is just the principle of detailed balance. This is what in thermodynamic equilibrium, if you have a thermodynamic equilibrium and you have a gases in Maxwellian distribution, for example, what does it mean Maxwellian distribution? Maxwellian distribution means that if you have a distribution like this Maxwellian, and you come to an energy bin between E and E plus delta E, what does it mean? It means that the nuclei or the atoms here in this room, they collide with each other and they have a distribution of energy. Let's assume that this is F of E and this is E. If we look at with a binocular and we look at all the molecules in this room, we will notice that the most probable at energy kT. The energy is kT. Okay, guys? And the average energy is half kT for a Maxwellian distribution. But what does it mean Maxwellian distribution? It means that if we assume the space now is not a physical space, it's energy space. So if we assume that we have a distribution of energy and we look at a cell of energy and we try to imagine that we focus over the molecule to look at the molecule and then look at this cell of energy, we will notice that what's inside this cell of energy is always constant. Although there is visitors coming to see you in the cell from scattering, whether it is up or down, they're coming to shake hand. At the same time, people who stayed for longer enough time, they will say goodbye and they will leave the cell, so that you will have constant number of particles inside the energy cell or the energy bin. So this is, it says that I have at this energy bin constant number no matter what. This is why this shape does not change. So if you have a temperature T, this is the Maxwellian and temperature T. If you increase the temperature, the Maxwellian will broaden. If you decrease the temperature, the Maxwellian will narrow. But at any given temperature, the Maxwellian has the same distribution. It means that at this energy, you make collisions, so you lose some of your, let's say, tenants of the cell. You will tell them, okay, you violate the law of existing in this cell, goodbye. Goodbye. We have to find another guy who will abide by the rule. Then we will bring some new people from there, but if the room or let's say the building has, let's say 100 rooms, every room has only one, so you have 100 people. If you kick 50, you will get 50 more, so that you will have no vacancy sign, and this is the no vacancy sign here. You do not accept any more guests to the room at this place. If you accept, you will have either deficiency or you will have increase of the number, and the shape will change, will be distorted. Did you agree with this? So this is what do we mean by Maxwellian. So this is exactly the same. So the principle of detailed balance, principle of detailed balance tells us that no matter what's the shape of the scattering cross-section, this is scattering cross-section, we will always have the following. We will have sigma scattering, no matter what's the shape of this, from energy E prime to the energy E multiplied by the flux, but the flux is just the velocity prime multiplied by the number, and number from a Maxwellian is m of E prime, and temperature T is always equal to sigma of E goes to E prime multiplied by the velocity V multiplied by m of energy E and temperature T. So this is the principle of detailed balance. Sigma scattering multiplied by the probability that you will go from energy E prime to energy E multiplied by the flux at this energy E prime, which is just flux is in V. And V is here, and N, the author wrote it as M because this is the number of particles at energy E prime and temperature T, which is a Maxwellian distribution. So you will notice that this is the detailed balance, principle of detailed balance. It states that whatever is scattered into this energy bin is equal to whatever comes out. Whatever comes in is equal to comes out. If you look at the Maxwellian distribution, you will notice that if you substitute with the Maxwellian distribution here with the form of the Maxwellian distribution, it will fulfill this principle of detailed balance. So substitute with M, I will give you the formula for M. You will notice that the right hand side is equal to the left hand side. So this will give us that M of E and T is a Maxwellian distribution, and it is given by the formula 2 pi over pi kt to the power of 3 halves multiplied by square root of e to the power of e over kt, where kt, k is Boltzmann constant and t is the temperature, e is the energy of the particle, and again k is Boltzmann constant, which is 1.38 10 to the power of minus 23. This is Boltzmann. So k is just 1.38 10 to the power of minus 23, and it is joule per what? So joule per what? Per degree Kelvin. Okay, guys. So now, without getting into the physics and the mathematics and all this stuff and deducing this, we just do some thought about this, and this leads us to the principle of the tilt balance from thermodynamics, and this gives us a good distribution function that fulfills this principle of the tilt balance is the Maxwellian. So now we knew that the neutron distribution has the form of a Maxwellian distribution. Sometimes, by the way, this is M of E and T. In the book, they can also write it as M of V and T. Okay, guys, M of V and T. And you have, in order to transform between M of E and M of V, you knew that the total number of neutrons scattered between energy E and E plus delta E is the same scattering between velocity V and V plus delta V. Yes, guys? So you knew that M of E and T, let's say, usually they write it N of E dE equal to M of V and T delta V. So you can get one in terms of the other. So if you have M of V and T and you want M of E and T, so M of E and T is just equal to M of V and T. You will substitute with E equal to half mv square, so V equal to 2E over m. You will substitute in every V by 2E over m, and then you will differentiate dV by what? By dE. So dV by dE is equal to what? 2 over m. Oh, this is under the square root. So so it will be 1 over the square root multiplied by 1 over the square root multiplied by whatever the differentiation inside the square root. Okay, guys? Sometimes they wrote, there is n here, by the way, guys. There is n, and there is, I messed up, there is a 2 over m to the power of half, where n is the total number of neutrons. If you have a billion neutrons, so this is billion neutron. If you have whatever number of neutrons. Okay, guys? Sometimes they wrote the 2 over m plus this constant here, all this constant here. Sometimes they write it as phi thermal. Phi thermal multiplied by phi thermal multiplied by kT to the power of square. So all this is phi thermal multiplied by kT to the power of square, because he wrote it as, let me rewrite it to you here, guys, so that you can figure it out at home. Phi thermal multiplied by E over kT to the power of square so this is the equation. Now, for this Maxwellian distribution, the most probable energy is kT, as I just stated early. Most probable What does it mean most probable? Huh?
The energy most particles have.
Yes, most probable is not the average. Most probable means the highest distribution in your particles. This is the energy that the majority of your population has. So this is the maximum here of the population. So the population will have this energy. This is the most probable. Usually the average will be shifted. So if this is the most probable, the average will be shifted here. And there is something else called median. And the median is the energy where the area under the distribution will be equal from both sides. So if you have something like, if you have it here, it means that this area, which is the number of particles here before it, is equal to this area, which is the number of particles after it. So this is the median. Okay, guys? This is from statistics if you happen to have any class in statistics. But what's the assumption that we did? What's the assumption that we did? No absorption and no leakage. No absorption and no what? No leakage. Yes? But this is not true. In nuclear reactors we have what? Absorption, and we have leakage. And there is lots of distortion mechanism that we have to look at here. So most of the absorption cross-section, usually for the majority of the nuclei in nuclear reactors, goes like 1 over V, where V is the what? Velocity. And this is why they call it 1 over V absorption cross-section. So usually, if you look at the cross-section as a function of velocity, and this is the velocity, it will be like this. And this is called what? 1 over V absorption cross-section. So usually it goes like this, which goes like what? 1 over the square root of what? 1 over the square root of E. So what does it mean? What does it mean? At low energy, what will happen?
Absorption
Will go high. So if you absorb, you have a shark. Let's assume that we have something like, we have a building, 10-story building, and then we build the building so that it will have 2 stories under the water. And under the water, the guys in the 2 stories under the water, or the 3 stories under the water, they have just a glass walls. They are looking for the Miami Beach, but from under the ground. And then all of a sudden, we shut the glass and let the shark get in. So you are terminating your low energy visitors or people in the low energy cells. Yes? Whoever will survive will say, and so on. Yes? But nobody will come from up to the downstairs. Yes? Exactly the same. You have neutrons here, and you have your sharks coming to eat them, but the sharks at what? At the low energy levels, because I have my shark open its mouth at the low energy. Needs to eat the neutrons. Yes, guys? So this is why you will shift your Maxwellian toward the high energy. And this phenomena is called absorption hardening. You are hardening the flux. Okay, guys? So this phenomena is called what? Absorption what? Hardening. Because I am hardening my distribution. What does it mean? Hardening the distribution. You make it move to the harder energies, higher energies. You reduce the number that populate at low energy by letting the sharks violently eat them. All of you, of course, happy to eat them. Then you will move to the upper energy level. Okay, guys? So this is the shift in this absorption hardening. So the shift to higher energies can be represented by approximately a Maxwellian with effective neutron temperature. So in this case, it's no longer the Maxwellian distribution, but I have to. The Maxwellian distribution is what? If I ask you, the Maxwellian distribution is a function of two parameters. What are those parameters? Not parameters, one parameter, but variable and parameter. The parameter is temperature. The variable is energy. So it's a function of one parameter, which is energy. Now, the parameter is the temperature of what? Medium. The temperature of the medium. But it does not matter the temperature of the medium because the sharks is there. Yes? So now I have to define an effective temperature, okay, neutron temperature, that will eliminate the fact that there is sharks over there and will enhance the distribution, this distribution. So this is called Maxwellian with effective neutron temperature. And the effective neutron temperature, Tn, is just equal to T multiplied by 1 plus C multiplied by sigma absorption divided by Xc multiplied by sigma scattering. So if sigma absorption, there is no absorption, and there is no sharks, and there is no bullet that you will hit the wall. So this is 0. So what's the temperature now? Which is the moderator temperature. This is the moderator temperature. This is the water temperature. So the neutron temperature will be the moderator temperature. Okay, guys? And C should be calculated experimentally. Okay, now let's see what's the effect of leakage. What do you think the leakage will do? The opposite. So now assume that the upper residence in our story building, a tall story building or high story building, it is now from glass, and we got a crazy guy with helicopter and hit the glass at once and kick those residents out. So those have the highest potential energy. The guys upstairs, they are gone. So what will happen for our distribution now? So this energy here will be what? Will be cooled. Yes, will be cooled because of this. Okay, guys? So because of the diffusion and leakage from the system, there is cooling for your Maxwellian distribution. Okay? So now we can represent the sigma absorption by sigma absorption plus a leakage term. And this is coming from the leakage term, D plus B square. Okay, guys? Why I put D? Why I put this? dB square. Because the non-leakage term is what? 1 over 1 plus L square B what? B square. And what's L squared? D over sigma absorption. Yes? So we can multiply sigma absorption here. Yes? And sigma absorption where? Here. But this is the non-leakage. 1 minus this is the leakage. So the leakage will be now equal to what? Sigma absorption plus dB square divided by minus sigma absorption divided by what? plus sigma absorption. So the leakage term is proportional to what? dB square over sigma absorption plus dB square. So this is why we can just replace sigma absorption by this term. Okay guys? And D is just proportional to 1 over 3 sigma transport, and sigma transport is the transport cross section. So leakage will preferentially remove higher energy neutrons, and this will offset the effect of what? Absorption. So absorption tends to shift to higher energy, but leakage tends to shift to what? To lower energy. Okay guys, in the slowing down region, if you remember, in this region, in the fast energy region it was what? Chi. Then it goes like what? Like this. Then it goes like what? Nope. 1 over E here. So somewhere at the 1 electron volt range, this is a Maxwellian which goes like e to the power of minus E blah blah blah, and it should meet 1 over E. So we have to have continuity of these two functions. Okay guys? Okay guys? So the flux, the Maxwellian, if we want to modify our Maxwellian distribution to give us the true distribution in the reactor, we should include the absorption, which will harden. And what's the effect of absorption? Adding Maxwellian at neutron temperature instead of moderator temperature. We should include the what? The leakage by just modifying the sigma absorption by sigma absorption plus D plus B square. Then, because the flux in the slowing down region is just goes like 1 over E in the slowing down region, this will tend to make the flux 1 over E, and Maxwellian flux must be corrected by adding a joining term. We call it joining term. So the joining term is delta. It's a joining term to join what? The Maxwellian to what? To the 1 over E slowing down flux. SD is slowing down. Okay guys? And this term here, this term, the delta, this term is nearly 1 when the energy E over KT is greater than 10. So if your energy over the most probable energy is 10, that you are 10 times this energy, maybe here. So this delta will go to 1. Okay guys? And this delta will nearly be 0 if the energy over KT is less than 5. So if you are less than 5, you do not add anything to the Maxwellian. Okay guys? So how we will add it? Here is how we will add it. So the flux as a function of energy E is just phi Maxwellian of energy E, and now we modified the Maxwellian by the neutron temperature to include what? The effect of what? Absorption. Plus lambda delta of energy E over KTN divided by the energy E. So now, if E over delta KTN is greater than 10, So this delta is what? Is 1. So this term will be what? 1, and I will have lambda over E. So my Maxwellian would be modified by 1 over E after 10 kT. If this is less than 5 kT, this term is what? 0, and I still remain with the Maxwellian. Yes, go ahead.
Is the temperature over there Tn, or is that the temperature to decide if it's less than or greater to?
This is the normal temperature. The normal temperature to modify the Maxwellian, not the Tn. Okay, but again, you will not. Yeah, go ahead.
Is that delta? Are you saying that's a function of E over?
Yeah.
Okay,
It's a function. It has a functional form.
Oh, so it's a common, not a square.
So if you just try to see what this functional form, you will have what? 5 what? 5 kT and what? 10 kT. Here is what? 0. And here is what? 1. I don't know what's in between. Maybe somebody sitting there. I don't know what's in between. Okay, guys? So what's lambda? Lambda is just phi thermal that I just defined for you. And this is pi over to 1 minus Z sigma scattering over sigma absorption. And this is called normalization factor. Okay, guys? So the flux now as a function of energy will be just phi Maxwellian plus lambda over E for E over kT greater than 10 and phi Maxwellian for E over kT less than 5. Okay, guys? Then we will be more than happy now to end the story of this, not the chapter, but just the 3 region of moderation, and we'll be just plotting the 3 region now that we talked about them early beginning in the class or in this lectures. So this will be the flux as a function of energy, and you have a Maxwellian but it's modified by 1 over what? 1 over L. Then you have some chi square or so. So this is chi of E over sigma total of E. If sigma total at a high energy is constant, it will be just chi of E. Then you will have 1 over E here. Then you will have the Maxwellian of E here, and the Maxwellian will be modified by the Tn and modified by the absorption hardening and diffusion what? Or leakage cooling or diffusion cooling. Okay, guys? So this is usually the cutoff for the Maxwellian is 1 electron volt. The cutoff for here is usually 100,000, and the energy here is up to 10 MeV, but usually, of course, the normal Maxwellian should go like what? Yes? This is the normal Maxwellian. And this is at here, it's just Fm plus lambda over E. Okay, guys? And this is a Fm or phi m. So the Maxwellian distribution has some useful properties. So if we have a 1 over V absorber, and this is one of the problems, homework problems, I think I give it to you, that if you have a sigma absorption that goes with 1 over V or goes like 1 over E under square root, for example. So sigma absorption of E and T equal to sigma absorption at energy E naught, different energy, for example, we can evaluate this as at what? Energy E naught. Usually E naught corresponds to a velocity of 2200 meter per second, and this is why they call it sigma absorption. At this energy, they call it the 2200 meter per second cross section. And the flux evaluated at this velocity, it's called the 2200 meter per second flux. So this is equivalent to, I think, 0.025. I think 0.025 electron volt. So you can calculate sigma absorption at E and T is equal to sigma absorption at E naught multiplied by V naught divided by V, or vice versa, sigma absorption at E naught multiplied by E naught divided by E. Okay guys, if you want to calculate the total absorption rate in the thermal energy region, is equal to what? From 0 to E thermal, and then will be what? Sigma absorption as a function of E and temperature T multiplied by N multiplied by the flux. This is the what? The Maxwellian here as a function of E and Tn dE. Okay guys, and if your cross section is 1 over V absorber, if it is 1 over V absorber, it will be sigma absorption at E naught, V naught, N naught. So it's very simple. If your energy cross section goes like 1 over V, so that's it. If you want to calculate all the absorption in the thermal energy region, when you substitute with sigma absorption equal to sigma absorption of E naught, it will be outside the integral. V naught over V, V will cancel with V, and you will have V naught will get out in not initial. Then you will integrate over the whole Maxwellian from 0 to E thermal. If you integrate over the Maxwellian here, it will give you a fixed number. If it is normalized, it will give you what? 1. So this is why you get this formula.
V naught over V, velocities.
Yeah, velocities. For a non, and again, phi thermal that I just talked to you about a couple of minutes ago, it's just 2 over the square root of pi NV. This is a very useful formula. So instead of just NV is the flux, it's 2 over the square root of pi NV. And very useful formula before we will leave. I will write it here, then we will leave. Is sigma absorption thermal. If it is non 1 over V absorber, it's pi over 2 multiplied by T naught over Tn. T naught is the energy of interest, let's say 2200, which is 300 degree Kelvin. So the temperature at 300 degree Kelvin, which is corresponding to 2200 meter per second, corresponds to 0.025 electron volt. You will calculate the absorption cross section at this energy, and this is the neutron energy corresponding to the Maxwellian, if this is not a 1 over V. So now we conclude with the most sophisticated part. Next time, I know that there is still sophisticated part, but next time, what's the part of energy or energy region that we neglect so far, we did not talk about? What do you think? What we are missing here to handle?
Between 1 over E in the past.
No. It's in the epithermal, there is a phenomena that we did not talk about. Resonance, which is extremely important. So next time we'll talk about the cross section and resonance and how to do it. Yes.
That should be the square root of T naught over T naught.
You want to help me on
Square root of what?
15
T
Yes,
naught over T
yes,
naught.
yes.
All right, I gotta turn my homework in. Supposing help.
Yeah.